Hey again, everybody. Mr. Armke here with you for CTI 120. This is the last lecture chapter for our first half, so the networking section. A little bit of a bonus chapter. Originally, the information that was included here was set up as part of a couple of other chapters, just a little piecemeal here and there. But they found enough information to consolidate it into its own section. So let's get into wide area networks, the fundamental basis of the internet at large. We're going to identify some fundamental elements of WAN service options. We're going to compare and contrast layer 1 and layer 2 WAN technologies, as well as the most common wireless WAN technologies. Now, a WAN, or wide area network, is a type of network that traverses a significant distance, and it is essentially built to connect LANs together. So LAN being local, W being wide. This is the bridges, the highways, if you will, that will connect the little towns and hamlets of our local area networks. The type of WAN we need in a particular implementation is based on the load of traffic that it's expected, the budget of the people who are implementing it and maintaining it, no less, the geographic breadth of coverage, so how much distance are we actually covering, and the commercially available technology to perform the implementation. Now, LANs and WANs, as you might imagine, have several distances. We wouldn't bother putting them in separate categories if they didn't. LANs connect nodes, individual hosts, and intermediary devices. LANs connect groups of those devices through default gateway-based routers and other types of host interconnections over a wider geographic area. LANs tend to be, campuses, something like Cape Fear or UNCW. LANs and WANs both use the same protocols from layer 3 and up, but at layers 1 and 2, we're going to vary slightly in terms of our access methods, topology arrangements, and media usage, so our actual connections in between. You're very rarely going to see somebody who uses a fiber optic connection to go from a switch to a host, but going between WANs, fiber is pretty common. LAN wiring is often privately owned. WANs are traditionally owned and operated by telcos, telecommunication carriers, for those in the know. They're also called NSPs, network service providers. So when we think of an ISP, we're thinking about an internet service provider for an individual or for a company. NSPs deal with the larger, what we call a tier 1 ISP infrastructure. So AT&T, Verizon, Charter, Comcast, Adelphia before they went down, essentially those were all NSPs. Those were the big ones. So people who were what are called tier 2 and tier 3 ISPs would actually lease access information from the NSPs. So a WAN link operates as a connection between one WAN site and another, often referred to as endpoints. Now these connections can be from one site to another, or multi-point, to where one site is connected to 2 or even more sites. So we can see on the right-hand side here, this graphic 12.1, the difference in scale between a LAN and a WAN. So where we have, a router that contains all the traffic from a web server, a switch, and several clients, a WAN is built on the links between cities and sometimes between nations. We often have two different types of data transfer method that we talk about, DTE and DCE. Data terminal equipment, DTE, is the customer's endpoint on the WAN, and it communicates there. The DCE is the carrier's endpoint for the WAN. So DTE is local, DCE is the wide area. The primary categories of WAN connections are as follows: a dedicated line, which is a continuously available communication channel that is not shared with other users, or a virtual circuit. Logically, it appears to be dedicated to the customer, but it can be physically through any configuration in the carrier's cloud of assemblages. And these tend to fall into two categories, either permanent or switched virtual circuits. So when you hear about PVC and you're talking about networking, it's important to understand, are we talking about physical cable, polyvinyl chloride, or are we talking about a logical PVC or permanent virtual circuit? Switching determines how connections are created between nodes on a network. Circuit switching is where we have a connection established between two nodes before they begin transmitting data. Packet switched is where data is broken into packets before transport. So let's look at some data transfer methods. At OSI layer 1, we see that we've got things like dial-up, and that uses PPP over copper lines. ISDN does the same thing, except for it can also include frame relay at layer 2. DSL can use PPP, Ethernet, or ATM, and can use either copper or fiber optic. Cable broadband tends to use cable broadband standards as well as Ethernet with copper and fiber optic media implementation. Excuse me. Metro Ethernet tends to use either Ethernet or MPLS with copper, fiber optic, or wireless media implementations. That tends to be the broadest of the WAN technologies. T carriers, so if you hear about like a T1 or a T3 fiber line, that's what a T carrier is. Triple P, frame relay or ATM, copper or fiber optic lines. SONET, Triple P, frame relay, ATM, or MPLS, probably the most versatile. Primarily using fiber optic. We're going to talk about each of these in turn. So when we're dealing with a WAN connection problem, there are some steps to take before calling our ISP. Preventative measures, of course, can be implemented to avoid having the problem in the first place. The biggest is to know the difference between where our equipment is as a subscriber and the ISP's equipment. Regardless of whether or not it's on a particular set of premises, the ownership can be different. Now, if we have ISP equipment that is on site, that'll usually be part of what's called an SLA, service level agreement. If we have an issue about, regardless of who owns it and who's responsible, we'll usually go through what's called CPE, customer premise equipment. So the SLA will define what the CPE is. There's a lot of acronyms. That's why it's important to make sure that you don't fall into jargon too heavily when you're talking with customers, because there are a lot of acronyms that can cross over a number of different fields. Any equipment belonging to the ISP should only be serviced by the ISP's technicians, even if it's on our side of the DMARC. Important thing to note is that, this is kind of like a warranty. If we start messing around with someone else's stuff, we then become liable. And we're talking about equipment that costs in the tens, if not hundreds of thousands of dollars. Some common items found at or near the DMARC would be an NIU, or Network Interface Unit. There's also a version called a Smart Jack, which is a little bit more descriptive in terms of what it reports and can provide diagnostic information. Line drivers, and then CSUs and DSUs. Common issues to look for here are there's a problem with the interface. So, there might be something that's connected incorrectly, or there might be something that's spliced wrong. There's a couple of different issues that can pop up there. DNS, so there's actually a problem with the domain name server. The router is completely misconfigured, or you may see some interference. You may have some nearby equipment that's causing operational problems. Layer 1 WAN technology, also called physical layer, are traditionally things like DSL, ISDN, SONET, and T carrier. Broadband is the concept of taking multiple services over a single physical conduit. We've talked about that before. In a broadband WAN, cables and bandwidth are shared between multiple customers, and the ISP will make a best effort attempt to provide up to the advertised bandwidth. So if you have a particular bandwidth that you get from Charter or Comcast or whomever you use, you'll want to occasionally run a speed test, because you'll be surprised at the variation that occurs even a few minutes apart, because we have what is called a distributed asymmetrical system. Asymmetrical or asynchronous means that the balance between upload and download is not equal. And for most people, this is a benefit. Your download speeds should often be faster than your upload speeds, because how often are you uploading materials? And to what density, especially in comparison to your downloads. DIA, Dedicated Internet Access, is a symmetrical system. These types of connections are important for businesses that back up a lot of information to the cloud, or to even to an online server that they will control physically. These internet access links are dedicated to a single customer. So it's not a single individual, but it could be a corporate customer. PSTN, publicly switched telephone network, is a circuit switch network of lines and carrier equipment that provide telephone service. It's also called POTS. That's how I learned it, plain old telephone service. Originally, it only carried analog traffic, but today we also have digital data, and now instead of having manually controlled switches, if you think about the old days of people who were plugging wires into holes into a big, literally called a switchboard, that is now done by computers and can be done in a much more efficient method. The CO, or central office is where the telephone company terminates lines and switches calls between different locations. So if you look at a phone number, you have an area code, so in our case would be 910. My office number, 362, would be a local exchange, and then 7377, which is my office extension, is my individual interface. So there's a couple of different ways we can look at that. Kind of like with a MAC address, we have our vendor ID, or our OUI, and then we have our interface ID. And each half tells us different things. So the way the telephone network is structured is very similar to how the CO still responds in constructing not only analog but digital telephony. The last loop, or last mile, sometimes called local loop, is the portion of the PSTN that connects the residence or business to the nearest CO. So if you go driving down, for instance, 17th Street, you'll occasionally see these little orange or tan kind of like tubes. They almost look like barriers or little roadblocks. Sometimes you'll see them that look like boxes. They're these, metal boxes. Sometimes there'll be, an AT&T sticker or something similar on the side. Those are routing stations that go to your nearest CO, and they branch off to local residences at that point. So there are these little substations. The NIU, or Network Interface Unit, is the termination point at the customer's demarcation. And there are 3 examples of PSTN network technologies that we still deal with today, although they are mostly obsolete: dial-up, ISDN, and DSL. DSL is still used because it's the cheapest way to get a dedicated service line. Dial-up and ISDN, as they have mostly been phased out, are still important building blocks to understand how later technologies are used. So here we see the local loop portion of the PSTN. We see the CO, the remote switch facility, the network interface unit, also called a junction box in certain cases, and then the customer's home. So if you have an older home, you'll actually see where that junction box exists on the outside. Probably is made out of gray plastic and says Bell South on the side. Now, DSL operates over PSTN and directly competes with things like cable broadband and T1. It does require repeaters for longer distances, and the distance between the customer and the CO will affect your actual throughput. So the further the distance between the lines, we start dealing with attenuation issues. It does support multiple data and voice channels over a single line and uses modulation techniques in order to control the delivery and carrier signals to be able to pass information. So it's able to store quite a lot of information in the voice lines, and it has to be separated by means of filters. XDSL refers to all DSL varieties. ADSL is probably one of the better known ones. That is a faster download than upload, very similar to standard broadband. VDSL is a variable or very high bitrate DSL. It's also asymmetric, but it's a little bit faster. And then SDSL has our equal upload and download. Now this is good for servers and things like that. It maxes out at about 2 megabits per second, so you're not paying for a really fast service, but again, for certain things, it's a cost-benefit analysis. So here we can see a DSL connection. Customer's premises, we can see our DSL modem and our splitter that filters those lines. The DSL AM and the switching facility and the splitter there, and then the internet at large. It's all a series of filters, if you will. Now the path of an ADSL connection is to establish a TCP connection, move through your DSL modem, either internal or external. Your splitter is going to perform the filtering operations necessary. The modem will then forward that modulated signal to your local loop. The signal will then proceed over 4-pair UTP wire. If it's less than 18,000 feet to the CO, the signal is then combined with other modulated signals in the telephone switch. At the carrier's remote switching facility, then we go ahead and start separating our data and voice signals. The DSL AM, which is the access multiplexer, will go ahead and process differentiation of signals, and the request will be issued from the carrier's network to the internet backbone. So the back and forth there, that's kind of the transition point. Everything that goes backwards from that is how we would receive a signal that was being responded to. Cable companies have their own connectivity option based on the existing coaxial infrastructure we already use for TV signals. They're standardized by an international cooperative effort under a suite called DOCSIS, Data Over Cable Service Interface Specifications. So if you see something like DOCSIS, 3.0 or whatever else, you know that it meets a particular set of criteria. Traditionally, cable broadband operates at asymmetric speeds. 70 megabits download and 7 megabits upload is pretty common. I know that with my current service, I think I get 300 megabits download and 20 upload. And I think there's stuff that's even faster than that. There's like 600 or 800. We're starting to approach working with gigabit transmissions. But again, that's special modulation of the cable transmission signal. So 10 gigabits per second is the belief that we would be able to do full duplex or symmetric speeds with DOCSIS 3.1. The best uses, of course, are just standard web surfing. It's probably what you're using right now. Most cable companies employ fiber for their backbones for a significant portion of their own physical infrastructure. We haven't really laid fresh copper since the 80s. Fiber is a little bit too attractive, and it's definitely future-proofed. So the cost, the sunk cost, if you will, has become a little bit more resultant in a what's called paying dividends. It pays off over time. HFC, hybrid fiber coax, uses fiber optic cabling to connect to the distribution center, to distribution hubs, and then optical nodes near the customers. From the nodes, you can then do a coax cable drop that goes from that line to the cable modem. So very much like you would expect in your internal network, if we're talking about the 90 meters to the 10 meter rule, the 90 meters could be something very high quality to make sure it gets to the end, and then you can use just a standard 10 meter cable to go from your wall jack to your desktop. A cable modem is a portmanteau of modulation and demodulation, which is the introduction or retrieval of a data signal into a carrier signal, is going to deal with receiving signals via cable wiring, and it operates at layers 1 and 2. It may connect to your connectivity device, or it may be your connectivity device in certain cases. There are router modem combos that I've seen. Now, many subscribers will share the same local line and throughput using a cable modem. So you're basically just tapping in. That's why if you go through an apartment complex, sometimes it'll be included as part of your package, your monthly package, but it may not necessarily be the speeds that you want because you are sharing it with a lot of other people. Metropolitan Ethernet is one that I really didn't get a chance to play with much until I was in my late 20s, kind of experiencing that mostly, my later undergraduate stuff. Metro Ethernet Forum is an alliance of over 220 world organizations that are developing ways to send Ethernet traffic across MAN and WAN connections. Carrier Ethernet Transport, also called CET or SET, is an Ethernet-based transport solution designed to overcome the weaknesses of Ethernet outside of the LAN environment. And that's something that I really wasn't aware of, is that Ethernet is good for local area connection. You really want to make sure you're using something more along the lines of serial transmission for outside the LAN environment when you're doing WAN links. Metro Ethernet is advantageous in that there are streamlined connections going from one device to the next. It's cost efficient, it's very scalable, and it's a high familiarity prospect. A lot of the technology that we're already using is built for Ethernet frames, and Metro Ethernet is very similar structurally. T-carriers, developed in 1957 by AT&T, includes what are called T1s, fractional T1s, and T3s. The medium for T-carriers tends to be especially conditioned copper wire, fiber optic, which is preferable, then occasionally wireless links over certain ranges that cabling would be considered inconvenient for. A T1 line is going to connect branch offices and then connect directly to the carrier. T-carrier standards, CXR, uses time division multiplexing over two wire pairs to divide a single channel into multiple channels. So time division is where we say that on 100 milliseconds this is where you transmit, on 150 this is you, 200 this is you, that sort of thing. Fractional T1 allows organizations to use only some of the channels on a T1 line, which means that while they still get some of the advantages of a dedicated connection like that, they're only charged according to the number of channels that they use. So if it's a smaller organization and they only need half of what somebody else may need, then you're able to charge slightly less. The T3 allows you to provide 28 times more throughput than a T1. They're much more expensive, and they are used by much more intensive businesses. So these tend to be very strong backbone connections to the net. Voice services optimization. T1 supports voice in two ways. You can use what's called an ISDN PRI, where you have a T1 line with the channels slightly reorganized. And this involves using what's called an SIP, Session Initial Protocol Trunk. This employs VIP VoIP, excuse me, to create virtual connections over an existing data service. A lot of emulation with some of these high-speed stuff. T-carrier equipment, things like the Smart Jack, terminates a T-carrier line and functions as a monitoring point. CSU and DSU, we talked about those a little bit earlier. CSU provides termination for the digital signal, and DSU converts T-carrier frames into things that the LAN can interpret, because of course T-carriers use a slightly different frame structure. The multiplexer is going to be able to combine multiple signals from a LAN for transport over the T-carrier line, and then it also is able to retrieve combined channels into individual signals. So a multiplexer is very similar to when we're dealing with a modem, be able to multiplex and demultiplex. Sometimes that'll be referred to as muxing, by the way, if you've ever heard that referred to in video. So here we have a graphic of a T1 connecting to a LAN through a router. We see our internet cloud over there on the left. We see our Smart Jack, or little monitoring point. And then internally, we've got our router with the CSU, DSU, and multiplexer. The telephone switch and data switch are able to then interpret things internally for the LAN. SONET, the synchronous optical network, is a high bandwidth WAN signaling technique. Now let's look at some strengths. High interoperability with existing WAN technology, very fast data transfer, simple link addition and removals, and a high degree of fault tolerance. It has a reputation for being self-healing. It's able to self-correct potential erroneous operation. It's considered the best choice for linking WANs between countries such as North America, Europe, and Asia. So when we think about that, North America and Europe, that's several thousand miles of distance going between. And then from Europe to Asia, not quite as long, depending on which area of Asia you're talking about, specifically Russia. But you're able to cover, oceans worth of distance using SONET. SONET internationally is known as SDH, Synchronous Digital Hierarchy. SONET often traverses multiple ISP networks connecting through what's called the Internet Backbone, if you ever look up what's called OC38. On the transmitting end, SONET multiplexers accept input from different network types and format the data in a standard SONET frame. Multiplexers will then combine the individual SONET signals on the transmitting end, and a demultiplexer will separate the combined signals to translate incoming data back to its original form. Now, SONET transmissions rely on a timing scheme, and frames can travel without data rather than disrupt the schedule. So that means that they're constantly outputting frames, even if they're empty. SONET frames are also structured to be a consistent size, so there's not, jumbo or collision frames or things like that. That also includes information to indicate where the payload begins, so that way, if there are options involved in the frame, those targets can be included as part of the frame. Data rate of a SONET connection is indicated by what's called its OC, or optical carrier level. So that OC38 I was talking about, that's what we're kind of backing into. It's commonly used by large companies, long-distance companies that link metropolitan areas, and ISPs that want to guarantee fast, reliable access to the internet. It's also used in certain capacities by telephone companies connecting their COs, but with modern cellular systems changing over, it's a little bit less common with that. So we've talked about a lot of layer 1 stuff. Let's look at layer 2. Layer 2 layer 2 does have a few technologies that will traverse the network in order to connect 2 or more LANs. So things like frame relay, asynchronous transfer, and multi-protocol label switching. Frame relay is a group of protocols for layer 2 originally designed as a fast packet switch network over ISDN. Today, it's used as the layer 2 protocol for various circuit interfaces and media. Data Link Connection Identifier, or the DLCI, is the identifier that routers read to determine which circuit to use for the frame. Frame relay is connection oriented, meaning that it has to be able to have that handshake, if you will. If we look at the graphic here on the right, we can see 3 frame relay connections going from a main office to 2 branch offices to create 2 logical PVCs, one between the main office and each branch. And then we can see that the DCE switch is connected to the ISP network with the frame relay. The PVC, or permanent virtual circuit, means that the connections are established before data can be transmitted and must be maintained after transmission. The advantage here is we only pay for the bandwidth that we're going to use, and it's less expensive than other WAN technologies. That is not to say, however, that it is inexpensive by any means. ATM, or asynchronous transfer mode, operations occur at layer 2. Asynchronous communications, as from the name, means that nodes do not need to conform to predetermined schemes and specifying data transmission timing. Each character is transmitted individually with start and stop bits for messages incomplete or completed as necessary. This is also going to specify some layer 2 framing techniques. It has a fixed packet size of 48 data bytes plus a 5-byte header, creates what's called a cell. The packet size does require more overhead and decreases the potential throughput, but the efficiency of that cell compensates for the loss, so it tends to balance out. ATM relies on virtual circuits and is considered a reliable packet switching technology, where virtual circuits provide the circuit switching rather than relying on the physical circuits. It does allow specific QoS guarantees for time-sensitive and delay-sensitive applications. It's really handy to use. So here we can see a graphic showing QoS definitions over a point-to-point connection. We can see here that we've got VoIP and email servers on 2 sites. Email is considered low priority for QoS because obviously you're delivering a message. VoIP, you need to have that voice transmission be very smooth, so that's high priority. The ATM router is able to interpret that information and shift it accordingly, and then we see ATM gigabit switches going between the ISP networks. Then we're able to relay information effectively for both. MPLS, multi-protocol label switching, is going to enable multiple types of layer 3 protocols to travel over any one of several connection-oriented layer 2 protocols. It can handle a ton of different types of payloads. It's often used by ISPs on their own networks for moving one traffic from a customer site to another. And we can use packet switch technologies over traditionally circuit switched networks. MPLS labels will tell us information about where the router should forward the message next, as well as prioritization information. So again, if we're moving traffic from one customer site to the next, we're able to prioritize things a little bit differently than if it was from a quote-unquote external network. Wireless WANs are specifically designed for high throughput, long-distance digital data exchange. Cellular is probably the largest example of WANs that we currently use. It was originally designed for analog phone service, but now, after 2G started, we're actually able to do digital transmission going from 240 kilobits per second at 2G up to expected for 5G up to 20 gigabits per second download and 10 gigabits per second upload. Lightning fast, especially for the very moderate levels of data that most phones tend to require. We're going to use traditionally one of 2 competing voice technologies, GSM or CDMA. GSM is the global system for mobile communications, often referred to as the world phone. And then CDMA is very similar to TDMA, but it uses codes instead of using time division. The network infrastructure for these is considered to be based on antenna and base station size. An internal controller will then assign the mobile client's frequencies to keep them from overlapping one another. LTE, I often get questions about this, is a subset of 4G, so it's actually a sub-technology of that 4th generation. It's not a standalone voice tech. The size of the cell is going to depend on the network access method, the regional topology, the population, and the amount of cellular traffic presented. The MSC, or Mobile Switching Center, is sometimes also called an MTSO, Mobile Transmission Switching Office, if I recall correctly. Each base station is connected to an MSC by a wireless link or fiber optic cabling. So if we look here on the right, we can see the MSC connected to the central office as well as the individual base stations. The mobile client is able to transition from one base station to another based on triangulation. There are some basic access pieces, HSPA+ for 3G and LTE for 4G. Satellite is another type of wireless WAN. It was originally used to transmit signals across the Atlantic Ocean, where transatlantic cables were not really considered germane for large format transmissions. They weren't as reliable. Today, satellites are used for transmitting consumer voice, video, music, and other types of data. There are different types of satellite orbits that we may see. What are called geosynchronous Earth orbit satellites, and there's also what's called an LEO, or low Earth orbit. Geosynchronous basically means that the satellite orbits at the same rate that the Earth turns. So as the Earth is turning, the rate of decay of the orbit, the rate at which it falls back towards the Earth, is synchronized. So it's falling consistently at the same speed as the Earth is moving, so it's kind of falling forward as the Earth is rotating. It's the most popular. It means that the object in question is going to stay directly above its transmission site. Uplink and downlink is using a satellite transponder which sends a signal to an Earth-based transmitter. The typical satellite has 24 to 32 different transponders and use various unique downlink frequencies. The frequencies that are available and the orbit location are assigned and regulated, in the US at least, by the FCC, the Federal Communications Commission. So here we can see the satellite orbiting over Earth, staying in the same position over the uplink and downlink sites, which means that they are able to be calibrated and aimed specifically to each site. So we've got a couple of different bands, L, S, C, KU, KA, and the standard K. The frequency range that we most often see is going to be in the either L or S band for most stuff that we see. As we go higher and higher frequency, we're able to transmit theoretically over a longer distance. Satellites transmit and receive signals in any of these 6, and within each band, the frequencies used for uplink versus downlink will differ. Satellite internet services will allow subscribers to use a small dish antenna receiver or satellite modem, which will then exchange signals with the provider's satellite network. This is traditionally an asymmetrical range, bandwidth of course being shared across multiple subscribers, throughput being controlled by the service provider. The downlink goes from about 2 to 3 megs, and the uplink is about 1 meg. Now, the reason that people still use this is because it doesn't require running thousands of dollars worth of cable. The upside there is that you get a connection at all versus nothing. Unfortunately, it's just that we haven't found a way to update satellite technology enough to make it a strong competitor with standard terrestrial broadband. So that is chapter 12, and that is the end of our first section of the lecture series. When we get into our next section, we're going to be talking more so about the security, the 6 chapters that we have for that section. So if you have any questions or concerns about that, you may, of course, send me an email at jearmke063@cfcc.edu. Or, of course, you can contact me via my Google Voice number, 239-7814. Other than that, I hope this has been an enlightening experience, and I will talk to you guys next class.